Okay, back again. All right, we're going to look at a couple more things. We're going to look at how the signal depends on pulse width. And then we're going to go ahead and do the energy relaxation measurement that we talked about a moment ago. Okay? Remember, from the handout, we know that if we make the excitation pulse very weak or very short in time, then the signal should be small. And that's what we've done, not too surprising. Now, as I turn this knob, I'll make the excitation pulse longer and longer. And what I expect is that at first, the signal should get larger, and you can see it getting larger now. Okay, and then it'll reach a maximum. And that's what's called a pi/2 pulse, where we've rotated the state vector by 90 degrees from the low energy state to the superposition state, or from the z direction to the x direction. And at this point, when we let the system go, the spin direction will precess by the maximum amount. We'll see a maximum signal, okay? But now, what happens if we make the A pulse even longer? If we make the excitation pulse still longer? After this maximum, the signal will get smaller and smaller as we increase the width of the pulse, until finally, here, it's almost vanished. Now we've excited with a pi pulse. That is, 1 second please. From the initial state vector, which was pointing in the z direction, we've excited it through this point up to this point. So now it's pointing in the minus z direction. Correspondingly, we've excited the population from the ground state entirely to the first excited state, okay, the upper spin state. When we release the system here, there's also no signal. So there's no signal after a no pulse, but there's also no signal after a pi pulse. The maximum signal comes after a pi/2 pulse. We could continue to increase the signal, the pulse length after that, and get a 3 pi/2 pulse, but that's not very important. So let's set this back for the moment to a pi/2 pulse and stop there. Okay, now we're ready to do the to measure the T1 time using the 2-pulse sequence that I explained a moment ago on the blackboard. Ready? The first thing we're going to do is we're going to zoom out a little bit. I'm going to change the oscilloscope scale, like so, okay? And now we're going to add a second pulse, a B pulse. Let me turn that on. It's off screen right now. Let me just move this over. There it is, okay? There we go. Okay, there's the A pulse. There's the B pulse, the second pulse. And then there's actually something over here we'll talk about in a few minutes. Now for the T1 sequence, we want the first pulse to be a pi pulse. So let's adjust this so that its magnitude goes to 0, or as close as we can get to 0. There we are. And then we want the second pulse, the B pulse, to be a pi/2 pulse. This one is a pi pulse, that one is a pi/2 pulse. So we'll make the signal as large as possible there. Okay? There's the B pulse. Notice that when we do this, we also get a third pulse we'll talk about in a little while. That's called the spin echo, but it's not important right now. So what we expect is that if we make the delay between the A pulse and the B pulse larger, the signal at the B pulse will get smaller and smaller and smaller and reach a minimum. And then if we keep making the delay longer, it will start going up again. Let's see if we can find that. So to do that, I'm going to start making the delay larger. There we go, larger. Well, I don't really see any change yet. We're going to have to do something even bigger. Now, there's a trick we can play to make this easier. I'm going to synchronize the oscilloscope on the B pulse. There we are. Now we're synchronized on the B pulse. Move that to the center of the screen. Now I can adjust the delay without having to keep adjusting the oscilloscope. So that's 6 units, 7 units, 8 units, 9 units, 10 units. Still not really changed. 20, 30, a little smaller, 40, 50, 60, 70, 80, 90. Oh, it's very small there. 100, up, that's back to 0. Okay. It looks like we have to go still larger. Give me a second here. There's one. Oh, There's 100. Hmm. Hmm. Okay. Excuse me. Oh, okay. That's 9 units, and that's 10 units. Okay. Pause 1 second. Oh, sorry. Let's try that again. 20 units, 30 units, 40 units, 50 units, 60 units, 70 units, 80 units, 90 units. Oh, that's quite small. Now let's zoom in a little bit. There we are. Very small. And now let's start adjusting it in tenths. So that's 91 units, 92 units, 93. Oh, it's getting bigger again. Let's go back. And if we do some adjustments, we can find the minimum point. So forgive me my zooming around here. I think that's about it. So the minimum point seems to be at 8.74 units. Give us a second and then we can figure out how many seconds that is. We just have to interpret this display here. 1 second. Hi, everyone. Okay, so our careful measurement shows that this time, when this reads 874, is 87.4 milliseconds. So what I did is I just measured the time on the oscilloscope to be sure. Okay, let's stop here. And just to summarize then, what this means is that the half-life for the spins in the upper state is 87.4 milliseconds. And from that, you can get the T1. Okay?